Welcome back. Now the next question is, how do we solve this optimization problem in practice? Okay, what do we do about p theta and so on, right? So typically what is done is the following. Let's look at this. So how to solve the ML estimation problem? So typically what happens is the following. So now this boils down to two questions actually. One, let's write that. So one question is how to choose p theta. Second thing is how to solve the optimization problem. If anybody would have told you that study 3 math topics and you can study any engineering topics, and these 3 topics are the vector calculus, probability theory and some optimization, they told you the truth, because most of the engineering applications are nothing but some applied version of these 3 foundations. That's it. So study these things very rigorously, so you can pick up anything. So that's the idea. You can adapt very easily. So two problems, right? One, how to choose p theta, and how to solve the optimization problem. And by the way, a bit of nomenclature. Um, See this thing, right, is also called minimizing the negative log likelihood. It's called NLL, negative log likelihood. Minimizing the negative log likelihood. Okay, and this thing, whatever I've written within these parentheses, is also referred to as the loss function. I will show you that when people talk about loss function from a completely deterministic standpoint, how is that exactly equivalent to minimizing NLL? That is what I will show you in a while, and this is called negative log likelihood, and you minimize the negative log likelihood to find the parameters, or you maximize the likelihood. Both of them are the same. Okay. Yeah, so I talked about loss function. So these two questions, right, how to choose p theta and how to solve the optimization problems are two questions. So how is it done typically is that for question A, p theta is chosen using a canonical function approximator. So what does this mean? We first assume a functional form on p theta. Okay, we can assume that p theta is a Gaussian distribution. The example is, right, let me write it in the next page. Example, depending upon the problem, okay, assume p theta is a Gaussian distribution. So whenever we say that it's a Gaussian distribution, it is parameterized by something, right? So make these parameters functions of these random variables. You can choose it to be identity. Okay, so you designate the parameters to this canonical function h of x. So this h of x typically is referred to as the hypothesis function or the model. I mean, again, these are nomenclature different. Some people call this hypothesis, some people call h theta as model or p theta as model, but it doesn't. Hypothesis function or model function. Okay. Now what happens is estimating p theta becomes estimating the parameters of this canonical function that we have defined. So just to jump ahead and tell you, this h theta can be a neural network. Assume this h theta to be a neural network and estimate the parameters of that neural network. So that's a canonical function that you are assuming there. Okay. And problem B, so optimization is mostly numerical. See, there are cases where optimization can be solved analytically. So, meaning you take the derivative of that log likelihood function and put it to 0 and parameters will come out, okay. But mostly numerical, because this canonical function that we will be assuming uh, is not analytically differentiable with respect to the parameters theta. For instance, neural network, right, if you take h theta to be a composition like neural networks, you cannot differentiate the likelihood function and put it to 0 and get your theta. So, you will have to solve it numerically. That is what we are going to see now as we move on. The underlying random variable, no? Data. This V is our data, no? We started with this data. So, this can be depending upon the problem. Suppose you are looking at estimating the marginals, then this V will be X. Suppose you are looking at estimating the conditionals, Y given X is what you are trying to estimate, then this V will be X. Okay, depending upon what your data is, it will be made the function of data. I will show you examples in a while. Okay, so let us look at a concrete example for this. Why? Oh, this I see. This is a Gaussian distribution, right? So I have made the mean to be a canonical function of some other function, and the covariance I have kept it as identity. I can make this as another function and estimate both of them as well. But for simplicity's sake, you only assume mean to be the canonical function and keep keep the other thing identity. Come again? There is loss of generality, right? This is, that's why I said this is an example of a particular model. I'll show you. I mean, like there can be multiple ways to do it. Huh? I'm just taking an example. So let us look at some one concrete case, right? So consider the problem of supervised regression. Okay, what does that mean? We'll say that shall we do it in one dimensions for ease? Okay, so I can make my x to be in RD and y is in R, and the data that I have is as follows. This is what I have. You want an example for this? Let's say that we are measuring the height, weight, and the amount of alcohol that one person consumes and the amount of food that one eats and so on. I just wanted a continuous variable. That's why I said amount of alcohol that one consumes. That's not discrete. I could have said whether or not somebody will do it, then it would be a discrete variable. I wanted x to be in RD. All dimensions are continuous. So you can make it 0 as well. Right? For me, it is 0, for instance. Right? So 5, let's say that there are 5 measurements that we are doing and y is the lifespan. You understood what the problem is, right? That's what we are doing. So it's a supervised regression problem. So somebody has measured that for 100 people and given how long they have lived, and for a new person we have to make that measurement and estimate how long they are going to live. Okay, so this is our data. Now what do we want to do? So we want to what are we interested in, by the way? So estimate. What do we want to estimate? We want to estimate the conditional of y given x here in this particular problem. See, now you see the generalization, right? It does not have to be pxy, py, anything. So it's the technique is applicable to any of the problems that you want to solve. So you estimate py given x. Now write down the likelihood, right? So let's assume p theta of y given x. Let's assume that this is a Gaussian distribution. So note that this is a Gaussian distribution in y. Why? Got the pun, no? So because it's defined, this density is defined on the random variable y, but it's a function of x because it's a conditional distribution. So what do we do is that we assume that the mean of this canonically is a function of x and its variance is identity. So this is our model. This is this is the assumption that we are making. Okay. Now, is it a good assumption? We don't know. I mean, it's as good as our assumption. That's it. It's a model. Remember my statement. No, all models are wrong. The question, we should not be asking whether it's a good assumption or not, good model or not. The question that we should be asking is this a useful model or not? And I will tell you the ways to quantify that later. How do you ensure that your model is useful or not? We will look into this whole idea of generalization, bias, variance, decomposition, and all that, which we will see later in the course. Okay, so this is a model. Py given x is this. Okay, now what shall we do? We will go through our recipe and solve the minimal KL divergence optimization problem. So we want theta star, and by the way, what is h theta of x here? H theta of x, what is this? No, this is a function, right? This is a function that is from x to what space? It's in RD, no? Remember that. It's from x to RD because the mean of this distribution, or is it so? R, no? Yeah, because it's one dimension. Because the distribution is over y, therefore the mean of that is one dimension. So it's a function from x to r, this canonical function. And what function should I use here? That's your choice. In fact, we will see 10 ways to do it. You can make it a linear function, you can make it a non-linear function or a composite, you can make it a neural network and all that. That is what we are going to see now. But yeah, so it is a canonical function. Oh, it's a 1 cross 1 matrix. See, that's the advantage of thinking in generalized way, no? You start looking at a matrix, a scalar as a 1 by 1 matrix.
How it is different from shifting a standard normal like we are shifting it by some factor mu.
Yeah.
It's a standard normal how it is, how can you estimate
Actually did not get the question.
The recursion.
The
distribution.
Which one?
Y given h theta of v.
Why is there h theta of v here? I don't see what is. This one, is it? This is not given. See, this is a semicolon. This is saying this is parameterized by this. So this is a distribution on the random variable y, and it is parameterized by h theta and I. That's what I'm saying.
That means it is mu.
H theta is mu. Yes.
Then we are just shifting standard normal.
Yeah. So the question that we are asking is, assuming that my p of y given x is a normal distribution, tell me what is the mean of the distribution is. That's the whole question that I'm trying to ask. Okay. Okay, so let's write things down. So we have to find theta star that would minimize what 1 over n 1 through n log of because we have n of them. So this is so I will skip the algebra. Okay, I'll just write this as proportional. I'll leave all constants. Okay, so we have log of e power yi minus h theta of xi squared, correct? See, whenever I run out of space to write in a page, I am reminded of this mathematician by name Fermat. Yeah, I don't know if you know the story. There was this mathematician by name Fermat. Okay, he wrote books where there were lots of theorems, and there was one theorem of his which is referred to as the Fermat's last theorem. Yeah, and that's a very simple theorem. All it says is you cannot have three integers that would satisfy this for n greater than 2. 2. 2 is Pythagorean triplet. You cannot find integers that would satisfy this. That was his theorem. It's called Fermat's last theorem. And he wrote the theorem and said that I don't have enough space in the margin of this book to write the proof, and did not write the proof. People after him, including the likes of Euler, tried to prove and failed, and this was for 3 centuries. And it was in 1990 that a British mathematician solved it and got Fields Medal for it. And the proof had math that was developed after Fermat's time. But Fermat wrote this theorem and said that I know the proof, but I can't write it because I don't have space here. So yeah, whenever I run out of space, I get reminded of, see, I just ran out of space here, no? So yeah. Okay, yeah. So this is what it is, and I'll skip the algebra again, and this will become the minimizer. There is a minus here, no? Yeah, there's a minus here, and this minus and the outer minus will get cancelled. Log and these things will get cancelled. Let me complete this. This will become does this expression seem similar? This is the least squares estimate. And we will show in the next class that you can deterministically write this and say that this is the loss function. So the minimum least squared estimate is an ML estimator, maximum likelihood estimator, under the assumption that the underlying conditional density is Gaussian with the mean given canonically with the hypothesis h theta of x. That is the statement. Okay, so I told you from this angle. From tomorrow, in the next class, I will talk from the other angle where I become the internet data scientist and say that there is x, there is y, there is a function, there is a loss function. You minimize that and just write this expression. That's it. You minimize this, right? So now the actual so-called mic drop moment is the following: that the MSE or the minimum least squared estimator is the estimator, is the maximum likelihood estimator, okay, of the random variable with the assumption that the underlying density is Gaussian with the mean equal to the hypothesis function. Okay, we will see that connect in the next class properly. So this is the end of this particular class. Thanks for attending. In next class, what we will do is, so this is one example. Okay, now what I will show in the next class is that this is the so-called loss function. If you change it and write it in the deterministic way, that always has a surrogate. It translates to the distributional assumption that we make on the conditional that we are trying to estimate. For instance, if I make this so-called loss function the cross entropy, okay, we make an assumption that the underlying distribution is Bernoulli with the parameter given by h theta of x. We will show that in the next class. So every model that you choose is the canonical parameter, and every loss function that you choose is the distributional assumption that you make on the underlying true density that you are trying to estimate. And all ML is minimizing the Keil divergence. Okay, this sets the context. From now on, it's just taking one form for h theta and solving that optimization problem, which is quite boring. These insights are the ones that are actually useful, right? I mean, at least I think so. Of course, human opinions differ in a very large way. So that's it. Thanks for attending today, and we'll look at the next things later.